Everyone, welcome back. We're going to be talking about non-homogeneous constant coefficient ODEs in this part of lecture. So, again, let's remind ourselves what it meant for a constant coefficient linear ODE to be homogeneous or not. So, we're only going to be dealing with constant coefficients here, so the AIs are all going to be just real numbers, and our Q of x is going to be a function of x. If Q of x is equal to 0, then it's homogeneous. Otherwise, it's not homogeneous. So let's give a couple examples of a non-homogeneous thing, because we don't know how to solve these yet, and that's what we're going to be doing in today's lecture. So y double prime plus 4y prime plus 5y is equal to 5, or y prime plus 7y is equal to 3x, or y triple prime minus y is equal to 3e to the x. So these are all non-homogeneous equations. So all these here. So now, how do we solve these? Well, let's start by considering the inhomogeneous equation. We know how to solve the associated homogeneous equation. And there's a very important fact, which is that if we have any particular solution to the inhomogeneous equation, and we know the general solution to the associated homogeneous equation, I have the wrong letter here. So this is an H. And we have a, so we can add those two solutions together, and that gives us a general solution to the inhomogeneous equation. Okay, so basically, if you have any solution to the inhomogeneous one, you can add that to a homogeneous equation, to the solution to the homogeneous equation, and that gives you a general solution to the inhomogeneous one. Let's see an example. So we have y double prime plus 3y prime plus 2y is equal to 6. Well, what's the homogeneous equation? So the homogeneous equation is y double prime plus 3y prime plus 2y is equal to 0. So if we try to solve that, you get y squared, lambda squared plus 3 lambda plus 2 is equal to 0 for our characteristic equation. Lambda plus 1 times lambda plus 2 is equal to 0. So lambda is equal to minus 1 or minus 2. And so the homogeneous equation solution is equal to c1 e to the minus x plus c2 e to the minus 2x. Okay? Because we have e to the lambda x as each of our basic independent solutions. And we also we need to figure out a particular solution. So I'm going to go out and guess. I'm going to guess that yp is equal to a, where a is some constant. So then yp prime is going to be equal to 0, and yp double prime is also going to be equal to 0. So we substitute those back into this equation here, and so you end up with 0 plus 3 times 0 plus 2a is equal to 6, which implies that a equal to 3. So we have a particular solution, yp is equal to 3. And if you plug this in, you'll notice that if you set y equal to 3, that this is actually a solution to the inhomogeneous equation. Well, then all you have to do is you combine all these things together, and you get a y general. So you get a y general solution. I'll oftentimes call that just y. Is equal to y homogeneous plus y particular, which is equal to c1 e to the minus x plus c2 e to the minus 2x plus 3. And let's try another example. So this one's a little bit more complicated. But one thing you might notice is that, well, our homogeneous solution is the same. So our homogeneous solution is still c1 e to the minus x plus c2 e to the minus 2x. And this is from the last slide, because all we did is we changed the q of x on the right-hand side. So let's guess a particular solution. I'm going to go ahead and give a guess that yp is going to be some constant times e to the minus 3x. So then we are left with yp prime is equal to minus 3a e to the minus 3x, and yp double prime is going to be equal to 9 times a e to the minus 3x. So from y double prime plus 3y prime plus 2y is equal to e to the minus 3x, that gives us 9a e to the minus 3x. plus 3 times minus 3 a e to the minus 3x plus 2 times a e to the minus 3x is equal to e to the minus 3x. Well, notice that these two cancel out, and so we're left with 2a e to the minus 3x is equal to e to the minus 3x. 2a is equal to 1, so a is equal to 1/2. And so therefore we have that yp is equal to 1/2 e to the minus 3x. Putting all that together, we get that the y general is equal to c1 e to the minus x plus c2 e to the minus 2x plus 1/2 e to the minus 3x. And let's put this all together. This is a general method. It's called the method of undetermined coefficients. So if we have this equation, how do we guess a particular solution? We know how to solve the homogeneous solution, but how do we get a particular solution for the inhomogeneous equation? Well, notice that whatever we guess for the particular solution yp, we have to take derivatives of it. A reasonable Ansatz, which is a fancy German word for a guess or an assumption, is that yp will look like the derivatives of q of x, but with different coefficients. So again, this is as we've done a couple times in this class. We're talking about the different ways to guess appropriate solutions, and then you solve to figure out exactly whether or not it's exactly the coefficients. So if q of x is equal to 5x squared plus 2x minus 1, then your guess is that it's going to be some constant times x squared plus some constant times x plus some constant. If you have q of x is equal to, say, e to the 2x plus 2x squared, then your guess might be, well, if you take the derivative of that, it's going to be a e to the 2x plus bx squared plus cx plus d, where those are all constants. Or if you have q of x is equal to sine x, well, yp is going to be a times sine x plus b times cosine x. So basically, whenever you're trying to guess the different parts of it that you have to solve for the coefficients, what you do is you take the right-hand side, so what the q of x value is, and then you take each of the parts of it, and then you try to take, then you take each of the derivatives, and each of those derivatives will tell you one of the pieces that you have to solve a coefficient for. Okay, so let's try this out. Guess an Ansatz. Let me reset the chat here. And let's say that we have q of x is equal to e to the x plus e to the 2x. What is our guess for yp? So remember, what we're doing is we're taking each of these pieces, we're taking derivatives of them, and we're putting them coefficients in front of them. So we're going to use a, b, c, d, e, etc. in capital letters. So what is the Ansatz? What is the guess for the particular solution? So what we need to do is we need to take what are the derivatives of e to the x? They're just e to the x, right? So you have some constant times the derivatives of e to the x, which is a e to the x, and you have some constant times the derivatives of e to the 2x, which are 2 e to the 2x, but the piece that you care about here is just the e to the 2x. And so this answer here is going to be C. Okay, it seemed like people were really confused by that. So if you have questions about that, you should ask. So basically, all we're doing is we're saying that when you look at the q of x, you can guess a particular solution by just looking at something that looks like the right-hand side. Let's try a different one and see if this makes a little bit more sense to you. So what about 3x squared plus sine x? So remember, you need to take each of the pieces on the right-hand side, so what q of x is equal to, and you need to take the derivatives of it and then look and then add coefficients in front of them, and that's how you guess the ansatz. Okay, so it looks like we have a couple people guessing A. So now, look, the problem is you have to be a little bit more careful, though. Because if you have 3x squared, what's the derivative of x squared? The derivative of x squared is 2x. So you have a piece with just x. And you also have a piece that's, if you just take the derivative, you have a piece that's just 1. And then when you take cosine x, you also have a piece that's cosine x. Okay, and so because of that, what this means is that you have ax squared plus bx plus c plus d times sine x plus e times cosine x. And so the answer here is actually D. And it looks like we had a pretty big mix of things. So you have to not only guess the things that look like the right-hand side, but things that look like the derivatives of the things on the right-hand side. Can I explain in more detail? Yes, I can. So, when you have something like 3x squared, so the piece we're looking at here is this x squared, right? But, so you have some coefficient with x squared. But the next thing you do is you take a look at x squared, and when we're substituting this back in, sometimes you take derivatives, right? So you also need to look for things that look like the derivative of x squared. And the derivative of x squared looks like things like x. And so that's why you have this x here. And the derivative of x looks like constants. And so that's why you have this constant here. And then we start over here, we have the sine of x. But then we also take the derivative of that, and we have cosine x. And so those are all different pieces. Well, you might take another derivative. When you take another derivative, you get sine x again. But then you already have that one. And so you don't need to worry. We take the derivative of this, that gives you 0, and so you also don't need to worry. Does that make sense? So that's how we do the pieces. Up here, this was easy, because the derivative of that was just e to the x, and the derivative of 2x is just 2e to the 2x. And so you don't get any new pieces. And I'm about to give you a much trickier one, and hopefully you guys will be able to figure this out. But it is a lot trickier, so let me just warn you of that right now. So again, remember that you have this piece on the right-hand side, and you need to take derivatives of it. And you need to keep on taking derivatives until you either start repeating them, or you end up getting a 0. Remember, it's derivatives, not integrals. So what's the derivative of 1 over x? Ah, yes, we have a brilliant question from Jocelyn. Can't it go on forever, Lon? And that should be a hint. That yes, it can go on forever. And unfortunately, that means that because it can go on forever, that means that this method doesn't work. So if the derivatives can go on forever, then this method just doesn't work. And of course, you need to make sure you take derivatives, not integrals. So log of x, I was tricky and put an a for log of x, because often you're like, oh, 1 over x, that goes to log of x. But that's only true if you're taking integrals, not derivatives. And so yes, the answer here is indeed e, because derivatives go on forever. Okay, let's do a couple more. Oh, sorry, let me give you, there's another important fact, which is what happens when you have a collision between your guess and your homogeneous solution. So what happens if your ansatz, your guess, looks like one of your homogeneous solutions? Well, then what we do is, just like with repeated roots, we just need to add another x onto it. So let me show you an example of this. So if you have y double prime plus 3y prime plus 2y, is equal to e to the minus x, well, note that y homogeneous is equal to c1 e to the minus x plus c2 e to the minus 2x. And therefore, our ansatz is yp is equal to, normally it would just be a e to the minus x, right? But unfortunately, e to the minus x and e to the minus already appears once. And so then instead we need an additional x here. Or if we have another example, so let's say y double prime plus 2y prime plus y is equal to e to the minus x. Well, the homogeneous solution to this is equal to c1 e to the minus x plus c2 x e to the minus x, because you have minus 1 as a solution twice. Well, our ansatz here is yp is equal to a e to the minus x. But this doesn't work because that appears there. So that doesn't work. So let's try adding another x to it. Ax e to the minus x. Unfortunately, that also doesn't work because that appears there. And so our actual ansatz is going to be yp ax squared e to the minus x. So basically, whenever you have a collision of this kind, you need to add an x to your ansatz. And let's go ahead and have you guys guess these things again. Let me reset the chat. So, if we have y double prime plus 3y prime plus 2y is equal to e to the x plus e to the 2x, what is your ansatz? And let me go ahead and give you a hint since this is the first one. So the first thing you need to do is you need to solve this, the homogeneous solution. Lambda squared plus 3 lambda plus 2 is equal to 0. So lambda plus 1 times lambda plus 2 is equal to 0. Lambda is equal to minus 1 or minus 2. And therefore the homogeneous solution is equal to c1 e to the minus x plus c2 e to the minus 2x. So what is your ansatz? Do you have any, does your right hand side look like your homogeneous solution? If so, then you need to add an x to it. If not, then you don't need to do anything, and you can just guess the ordinary ansatz. And note that for the purposes of this discussion, if you have a negative x, that is not the same as an x. Anyone? So it looks like we have a couple of D's, but you have to be a little bit careful, because do these things match any of these? Do they match? Okay, that's a little bit concerning. We might have to spend a little bit more time on this on Friday, Len. Because note that none of these match. E to the x doesn't match e to the minus x, or e to the minus 2x. And because none of these match, the answer is actually A. A e to the x plus b e to the 2x. We don't have any matches between the solution and the particular solution ansatzes and the homogeneous solution guesses. And therefore the answer actually is A here. Let's try another one. So y double prime minus y is equal to e to the x plus e to the 2x. And again, we start by solving the homogeneous equation, lambda squared minus 1 is equal to 0. Lambda is equal to plus or minus 1. So the homogeneous equation is equal to c1 e to the x plus c2 e to the minus x. And now the question is, how many of these things match? And if they match, you need to add an x in front of it. If they don't match, you don't do anything, and you just have the ordinary coefficient. So let me start by giving you the ordinary ansatz, which would be a e to the x plus b e to the 2x. Now the question is, do any of these things match? And if they do, you need to put an x in front. Okay, it looks like you guys are getting the hang of it a little bit. So this e to the x matches, and so you need to insert an x in front of here. So this is actually a x e to the x, because this piece matches that piece. And so the answer here is indeed B. And let me do one more. So y double prime plus y is equal to sine x. So again, we need to be a little bit careful, because we have, when we solve this, you get lambda squared plus 1 is equal to 0. So lambda is equal to plus or minus I. And so therefore the homogeneous solution is c1 sine x plus c2 cosine x. And since we're running out of time, let me just put down the guess. The normal guess is a sine x plus b cosine x, because those are the derivatives of sine x. Unfortunately, those match, and so you need to add an x in front. And so since we've added x's in front, we end up with this answer D here. Okay, let me finish off with one quick example, and then we will call it a day. So if we have y double prime plus 2y is equal to x squared, y of 0 is equal to 1, well, we can solve this by just saying, well, the characteristic equation is lambda plus 2 is equal to 0, and therefore lambda is equal to minus 2. So the homogeneous solution, y homogeneous, is equal to c1 e to the minus 2x. And what's our particular solution? Well, our particular solution here is ax squared plus bx plus c as our guess, because we had x squared on the right-hand side. None of the terms match, so we don't need to worry about adding extra x's. And so then yp prime is equal to 2ax plus b, yp, and when we plug that in, so we plug these in back into the original equation, and so you end up getting yp prime plus 2y is equal to 2ax plus b plus 2ax squared plus 2bx plus 2c is equal to x squared. And that's just taking this equation up here and plugging things in. And that leaves us with 2ax squared is equal to x squared, 2ax plus 2bx is equal to 0, and b plus 2c is equal to 0 by just equaling the right and left-hand sides with the terms. When you solve these, you end up getting 2a is equal to 1, a plus b is equal to 0, and b plus 2c is equal to 0. And you get a is equal to 1/2, b is equal to minus 1/2, c is equal to 1/4. Putting these all back in, you get yp is equal to x squared over 2 minus x over 2 plus 1/4. And that's just solving the for the general solution. So the general solution is y gen is equal to y homogeneous plus y particular, which is equal to c1 e to the minus 2x plus x squared over 2 minus x over 2 plus 1/4. And if you want to solve for the initial value, you have y of 0 is equal to 1, which is equal to c1 plus 1/4, which implies that c1 is equal to 3/4 when you plug in 0 there. And therefore, the final answer is y is equal to 3/4 e to the minus 2x plus x squared over 2 minus x over 2 plus 1/4. Okay, so let's putting everything together. And to summarize, if you have a inhomogeneous ordinary differential equation, you first compute the roots of the characteristic polynomial and get the independent solutions. They will either be of the form e to the lambda x, or this e to the ax cosine of bx, or e to the ax cosine sine bx. You can often guess a particular solution by using an ansatz with undetermined coefficients that looks like the derivatives of q of x, and then you solve for the coefficients. And the general solution is then given by the homogeneous solution plus any particular solution. And you can solve an initial value problem by plugging those values all back in. And this was a lot, so we will be going over this a little bit again on Friday. So this does complete this part of the lecture. So yeah, if you guys have any questions about the quiz, I will stick around for a little bit after class, but I will end the recording now.